So before we talk about inverse functions, let's look at a function that you have maybe seen before. So this is for converting temperature. So we can calculate temperature in degrees Fahrenheit by plugging in degrees Celsius into this function. So if I wanted to find f of 100, so my input would be C, and C goes right there. So what this would look like is f of 100 is equal to 9/5 times C, which we're letting be 100, plus 32. And if we plug that into a calculator, we'll get 212. So what this tells us is we input a value for C, and we got out a temperature for Fahrenheit. So this gives me a conversion. We just found that 100 degrees Celsius is the equivalent of 212 degrees Fahrenheit. So that's how this function works. It has this input of Celsius, output of Fahrenheit. So let's say I wanted to solve for Fahrenheit when Fahrenheit is 32 and I want to find what Celsius is. So how we do this is we plug in 32 and we're setting that equal to 9/5 times C plus 32. So what I would do is subtract 32 from both sides of the equation. So 32 minus 32 will give me a 0 for 9/5 C. And then my step here would be to multiply by 5/9 so that my fraction totally cancels out. Or you could think of that as like dividing by 9/5 is the same thing. And what we're seeing is C is equal to 0. So in this scenario, we got a C of 0, and we started with Fahrenheit of 32. So our conversion here would be 0 degrees Celsius equals 32 degrees Fahrenheit. So what I want to do in this next step is solve the equation, and so I'm missing some wording here. I want to solve this for C. Basically, I want to change this function so that how it's given to me at the beginning is input C, find F. What I want to do is be able to input F and find C, which we did do in this last example here in part B, but we had to do some maneuvering to get there. Instead, I want a more direct function like what we have for finding Fahrenheit. So what we're going to do is to solve for C, I'm going to subtract 32 from both sides of the equation. So that'll give me F minus 32 equals 9/5 C. And then I'm going to do that multiplication with 5/9 so that my fraction cancels out. So that on this right-hand side of the equation, all those values cancel out, and all we'll have left over is C equals, and then we have this, I'm going to leave that fraction factored out, 5/9 times F minus 32. Now what I have here is a function where I can input Fahrenheit and get this output of Celsius. And this right here is the idea of an inverse function. The idea that our original function, we were working with input of Celsius, and we would get an output in Fahrenheit. And what we did is we just got a new function where the input is Fahrenheit and the output is Celsius. So this new function would be called our inverse function from what we started with. Because what we did is we changed the operation where instead of having C be the input, it's now the output, and where the output was Fahrenheit, that would now be the input. So that switching of what we plug in and what we get out is an inverted function. So something we need to check is to make sure a function can be inverted is it needs to be 1-to-1. So that means that every y value that's in the range has exactly one x value. And you could think of this as that there need to be unique y values. And we'll talk about in terms of a graph how this comes through in a future video. So if it's 1 to 1, then what we can do is take the inverse of the function. And what that does is it reverses the process of our original function. In short, how to find it is that we are going to switch the variables x and y and solve for y. And we'll do that in an example right here. Our notation for an inverse function is we take the notation of our original function and put a -1 up there. I don't want to say it's an exponent because it's not. It's just notation to represent the inverse function. So like for this example down here, I have f of x, and where I see f -1 of x, I would say the inverse of f of x. So that's how I would read it out loud. The inverse of f of x. So I won't really say the -1 part because numerically it doesn't do anything. So with that, it just means the inverse. Okay, so how we're going to find the inverse function is my original function. If we replace f of x, we could think of that as y. So really I have this equation, y equals 2x plus 3. And what I'm going to do is switch x and y. So I'm going to switch it so that it's x equals 2y plus 3. And then I'm going to solve for y. So I would subtract 3 from both sides. So I get x minus 3 equals 2y. Then I would divide both sides by 2. So we end up with y equals x minus 3 over 2. And that's my inverse function. So what I get out of this, f of x, our original function, is the 2x plus 3. The inverse of that function, so the inverse of x, inverse of f of x, is x minus 3 over 2. Notice in our inverse function, it's like we reversed the operations we were doing. Where I was adding 3 in the original function, now I'm subtracting 3. Where I was multiplying by 2, now I'm dividing by 2. So it reverses those operations, or inverts them. Let's take a look at some of our composite functions of what happens when we layer an inverted function with the original function. So if we have the original function on the outside here, and we're plugging in the inverse function, which we just found as x minus 3 over 2. So f of x tells me to take 2 times the input plus 3, and the input is this x minus 3 over 2. Well, those 2's will cancel out with each other. So I have x minus 3 plus 3. Those 3's will cancel out, and we get x out. And we're just going to hold on to that thought while we go to this next one. So we're taking the inverse function of f of x, which is 2x plus 3. So our inverse function tells us to take the input minus 3 and divide by 2. And what we're plugging in is 2x plus 3. Well, in the numerator, that positive 3 and negative 3, we'll simplify those down. So we'll have 2x over 2. And those 2's will cancel. So we're just left with x. And this is a property of inverse functions. Like I was saying, how they reverse the process of the other function. Well, then when you make them composite functions, when you layer them together, it should all kind of undo itself. And it should undo itself in a way that you're just left with x in the end and nothing else. So this is a way that we can check whether or not we have the correct inverse function, or just whether or not two functions are inverses of each other. And that's that if you take f of the inverse function, that should equal x, and it should work for both of them. It has to work for both of them. If we take the inverse function of f of x, that should also equal x. So, some things we get out of this introduction is this definition of inverse functions, and we'll talk more about this idea of one-to-one. Making the inverse function, which we'll get a lot more practice with this, where you switch your variables, solve for y, and that gives you your inverse function. And then the property of inverse functions that we can check with composite functions, layering the original and the inverse, and that should always give x out.